Hello, I wanted to talk today about Rust modules in React Native. As you know, I do a lot of open source and I develop a lot of native libraries for mobile and React Native. And I've been seeing a wave of clients as of late that want to do Rust development, port their SDKs, libraries, other third-party libraries into the mobile ecosystem. So I thought it would be interesting to kind of talk about Rust, the challenges, the benefits, and so on, what I've seen in the last few months. So the first thing that you should know is that Rust is a native, modern, fast, memory-safe language. And that doesn't really tell you a lot why you should use that in your project. The really real question is like, okay, where are the real benefits and the disadvantages of using Rust? I'm going to tell you some from my own experience over the last few months that may or may not apply to your project. So one of the big reasons for me it's that it's easier to compile than C-based projects and some other native projects, just because of the tooling of all the previous tools. It's quite complex. Sometimes you might need to learn about Xcode, CMake files, build.gradles, etc., etc. And with Rust, you basically just have the Rust compiler. You have some extra crates that might help you compile for different targets and architectures. But it's basically just one command. You put your target architecture and it will just output your binary files. The tooling is great. Again, the compiler is fantastic, but also it comes with everything included. You have a linter, you have a formatter. The messages that you get from all the different tools are most of the time, they make a lot of sense, easier for you to debug. And at least in my experience, starting from very simple crates, it's easier to grasp than C and C++. The problem with C and C++ is that they have a lot of the compilers are very lenient, so they will just compile your code, but it's not necessarily correct, the best way of doing things. You might discover memory safety bugs at some point, and if you don't have 30 years of experience in C++ and have not read every single book out there, this is a serious security vulnerability. And a big benefit that I have seen, especially in the projects I have worked on, is that you have this unified core where most of the logic resides. And because it's written in Rust, it's fairly portable. You can compile it to different OSs and architectures. Even WASM nowadays, WebAssembly, it's supported. So maybe at some point you can even make it available on the web. So it's great if you are targeting a broad spectrum of targets. Okay, so what are the disadvantages of using Rust? At first, it feels great until you start hitting async code and threaded code. Then it gets really complicated. The primitives that are there are kind of hard to grasp. The threading model works, let's say, a little bit different than other languages. So there's a real struggle to kind of understand the code at that level. That being said, the compiler doesn't allow you to do unsafe stuff. So then again, it helps you not to shoot yourself in the foot. It just takes a lot of effort to get where you want to. You cannot call native Swift and Kotlin directly. That is if you're targeting the mobile platforms. But you do need to expose whatever API you're trying to call through a C layer. And at the same time, from your crate to the mobile platforms, you might need to create a C API for you to get access into the functionality of your crate. So we're going to see a little bit about the tooling in a little bit, what helps you there. But even if you need to write this manually, it might or may not be too complex, but it's one extra step that one needs to take. So I'm just going to go in and jump into creating a sample lib library, a lib crate. And we're going to go through some of the steps just to give you an idea of how would you do this. There is a lot of, let's say, scripts that need to be set up for you to compile the thing and then link it to iOS and Android and whatever platform you want to develop this. I'm not going to show you that because that would take too long. I'm just going to give you like the idea of how this works. So we're going to start by creating a lib crate, adding a C API. We're going to compile it to the target architectures. We get a binary out of that. Then this is the part where I'm just going to drop it into my project, and then I'm just trying to call it from one of the native environments. Okay, so I'm here in my console, and I'm just going to start by creating a new library. As you can see, I'm going to call this oplib, passing the library flag, and this is just going to create the folder with all of the files I need inside. So I'm using Rust Analyzer in VS Code that will take a look into my cargo.toml and try to compile the file and show me the types and the errors. And you can see here it's very empty. I have no dependencies right now. And I have this lib.rs, which will be the entry point for my library file. Here you can see I have a basic function, which is my add function, and a test module. I'm just going to skip all over this for now. And I'm just going to take a look into, let's say, an example exposed function for my library. So you can see I have added this annotation, the no mangle annotation. This is because Rust, like C++ and other modern languages, when they compile your code, they don't keep the function names intact. So once this gets compiled, it will be replaced to something random, let's say. So by using no mangle, I can keep the symbol table clean. So this can be called from from external sources. Then I add the extern C directive, which basically tells Rust this function needs to use the ABI of C, which allows other C programs and C functions to call. This has to do with bit alignment, pointers, etc., etc. I'm just basically telling the Rust compiler treat this function as a C function. Now, because this is an externally called C function, I'm marking my function itself as unsafe, because the compiler cannot guarantee necessarily that whatever is calling this function is following the right formats and ABI, etc., etc. I might be able to skip this actually. So if I delete this, yeah, it still compiles, but we will see later if at some point I need to use a pointer or something, then I need to use the unsafe keyword. Okay, so the next thing that I'm going to do is, now I have my function, but if you know a little bit about how C works, you need a header file that you can import in your own project so you can call these functions. And in order to do this, I could write manually a header file with my function definition, but that is very error prone. It gets tiring quite fast if you're changing your function definitions very often. So there's a little crate which is called cbindgen with help us. Cbindgen will just enter the entry point of your library and will start to crawl all the external C functions that you have added, and will automatically generate a header file for you. And in order to automate this, I mean, I could just run a command every single time that I want to generate this header, but there are better ways to do this. So one thing that I'm going to do is I'm going to create a build.rs file here at the root, and I'm just going to copy this. I'm just going to paste it here. So this is from another project of mine, but basically I'm just saying if the lib.rs file has changed, then rerun this entire thing. And basically I'm just going to call this generate C headers function. And my C headers function, well, right now it's failing because it's not finding the external crate, but that's fine. I'm just going to generate, I'm going to change this name into oplib. It has a auth guard. I'm just going to call this oplib and into a namespace. So basically what I'm configuring here is I'm telling cbindgen how should we generate this header, right? So it should be a C++ header. I could change this into a pure C. There are some differences in there. I want include guard, so it doesn't include more times. I want to add a warning. I want to have it with a namespace, and basically I just tell it generate. If it fails, fail with a message, and then just write it to a file. So you can see now here I have auto-generated header file. If at some point I were to change this definition, and let's say third, and this just takes another U64, I save it, then you can see my header has been updated. So now I have, let's say, the core of my crate. You can imagine at some point exposing all of the functions that you need. Now I just need to compile it in a way that I will be able to call this from my application. So I'm just going to go ahead and add this section into my cargo.toml, where I'm just going to tell this the crate type is going to be a static library. So I want to compile my library for all the different or as a static library to be linked at compile time within my system. And I'm just going to tell this to do a build in release mode, and I'm just going to pass the target. So you can imagine if I'm targeting Android, I need to pass all of the architectures. For iOS, there is some complexity there because you need to target iOS, the simulator for M1 versions and the simulator for Intel versions. But for now, I'm just going to compile this. It's going to do a bunch of compilation for all the basic stuff that it needs. And now if I go into the target folder, Apple iOS, you can see it has generated this lib oplib.a, which is basically the file that we can just drop into iOS and call our function by importing our header, and the linker will make sure that the symbols are there. Now, this is the part that I'm going to skip. There is a lot of moving parts that you need to take care of here. Not only you need to just copy and paste this .a file, because that's not how iOS work. iOS requires that you have a XC framework that kind of bundles together everything, and then Xcode can read that XC framework and make sure it's linking the correct version for the architecture you're targeting. Then you need to load that. If it's a static library, which I have just built, then it's automatically loaded whenever you load your project, your library, if it's on the dependencies. But if you have a dynamic library, then you need to take a lot more steps. You need to make sure that it's that it's signed, and Xcode knows how to read it, etc., etc. Lots of moving parts. So I'm just going to skip that for now. The tutorial is on my website. Let me just show you that for now. So if you go to my website and then you go to loading dylibs in iOS, here I give you the script, I give you a makefile, kind of detail all the steps that one needs to take to load dynamic libraries into iOS. Yeah, so there's a lot of steps here which are not super interesting right now. So I'm just going to jump ahead a little bit and assume that I have packaged my Rust crate, which is now ready to be consumed from my native module. This is another library, so it will be a little bit more complex to read, but we will just get to the point that we are trying to analyze, which is calling our Rust functions. If you have seen my other videos, you know I don't create turbo modules, so you will see a lot of kind of manual creation of the React Native module, but it doesn't really matter. Basically here I am just creating an object that's going to be exposed into the JavaScript runtime, and I call this function, and this is the function that injects my, let's say, native functions into the JavaScript context. And here you can see, if I click on this namespace, this takes me to the header I have generated previously. Again, this is for another library, so it's a little bit more complex. But basically, these are my Rust exposed functions. So you can see I have, for example, generate HMAC key, HMAC sign, HMAC verify. And from my file, what I do is just use this header file. Normally, so then let's say I just create a HMAC key. Then later I should be able to just call, let's say, where is the verify function? Here, for example, I have my HMAC verify. So if we follow the previous example that we were doing, something very simple, then here I would just have the op lib add, and then I just need to pass unsigned int, and then it should just work, right? This is in C++, so there is not a lot of problem. That's kind of the limitation. It's a C API. So if I go back into my source code here, and we just think about a little bit, okay, since this is a C API, you need to consider certain things, right? Unlike C++, passing, there's no smart pointers, there's no share pointer, unique pointer, memory management is a lot more, let's say, basic. So one of the good examples I take for following and creating a good C API is SQLite. And there you will be able to see, let's say, for example, functions usually return a status code. So if I go here into the my sign function, for example, it returns a status, and then this is usually 0. It's still for good hygiene of your library, you want to expose your codes as enums. So I just check, if it's not a 0, then it means something has to go wrong. And whenever you call your functions, you kind of have to pass error or a character pointer, so Rust can fill that error for you, and then you can return these errors into the calling context, and so on and so forth. Okay, so now you might be thinking, okay, that sounds nice, but it looks like it's a lot of work. There might be a lot of bugs. I can show you, however, this has been successfully deployed out there. Prisma, I helped them with their migration of their project, make it available for React Native, and this was kind of the playbook that we followed. They already had the Rust core that used to do all the logic of their queries and then communicated with SQLite. It also internally compiled SQLite from source, so we didn't need to link anything. Everything was kind of packaged. The only thing that we needed to do was, again, create this C API on top of the core, and then kind of just link it and make it available in a React Native module. This was successful. It's deployed. Prisma can do whatever they want with that. Now you might be thinking, okay, that sounds nice, but it also sounds like a lot of work, just creating a C API for every single function that my crate needs. If you're developing an SDK with a lot of functions, exposed functions, then yes, it can get tedious. However, there is some tooling now available that might make your life a little bit easier. One of these is called Unify. Unify is a bindings generator for Rust. It basically has a DSL-like language of doing things, of definitions, where you can just write your definition of the objects that you want to expose, and it will kind of auto-generate and bind to your Rust function. And one of the companies I work with, Filament, they have a lot of interest in writing their SDK, their core logic in Rust, and they have invested in expanding Unify to React Native. So basically what it does, it just takes the usual Unify definition file, and it will now auto-generate a turbo module for you. It will bind all the Rust structures and functions, everything that you give it, and will output a turbo module ready to be consumed from your JS classes. Now, also from my side, we just released a new library called AWS-LC. It's a mouthful, I know. It's the Amazon's Lib cryptography library ported to React Native. And the idea behind OP AWS-LC is not only to bring one more library into the ecosystem, but actually it has a very cool feature, let's say AWS-LC, which is basically it has FIPS certification, which means the US government has gone through every single line in the code base and ensured that this is cryptographically secure, right? So security, very important topic. The more certifications, the more eyes you have on your implementation, the better it is. And again, this was more of an exercise for me and my team to kind of practice Rust, creating bindings, the compilation, for them to learn a little bit more on how to do this. It's pretty bare bones. Right now, we only implemented one of the algorithms, which is the HMAC, which you already saw the code in the previous video. But the idea is to get maybe some sponsors, some investors. You know, if you need some other functions within the library, you just need to sponsor us for a little bit of work, and we will make it available for you. And again, this is one that has a Rust core, compiles into a library that then gets loaded in the runtime. And that's it for now. Of course, there are many things I kind of didn't touch. Implementation details, how to expose certain functions, how to follow certain patterns, do async blocking of execution of functions and whatnot. There are many details in there that you need to know once you're actually implementing Rust. But that kind of gives you the core idea of how do you get to run your Rust module within React Native, iOS, mobile platforms. Once you're there, you can also compile it to WASM. You just load it in your module. It's already should be already available to do, you know, heavy computation or animations and whatever. So yeah, looking forward to hear more about your questions and whatever suggestions you may have. Have a good one.